here, okay, standard position, initial side, terminal side, and coterminal angles. Okay, so this is just vocab about where something ends, where something starts, things like that. Okay, so like I said, in order to understand this better, we're going to take knowledge of a couple things we already know about. So something like the coordinate plane that has like an XY axis. But then to understand like what is 45 degrees or 360 when the announcer says, oh, like you just did a 360 or something, which these days apparently is not that exciting with all the tricks they were doing, right? So if he did a 360, you would all be like, oh, he went around the circle one time. So the circle is going to be here to help us understand those angle positions. So it would be like having a circle with a center at the origin of the coordinate plane. Okay. Sorry that my circle is ugly. Okay, so standard position is what we're going to talk about right now with the initial side and the terminal side. So basically our initial side is always going to be this positive part of the x-axis. So we're always talking about starting here. So that's our initial side. That means that that is at 0 degrees. Okay. So if somebody said, oh, put a 45-degree angle in standard position on this diagram, you would put its initial side on the x-axis, and then what you would do is you would go this direction counterclockwise, okay, for any angle that's given in positive. So if they said 45 degrees, you would go 45 degrees counterclockwise. So given that I know like here would be 90, I would say 45 would be about here. Okay? That this would be my 45-degree angle. So here is me drawing that angle in standard position. Okay? Its initial side is on that positive portion of the x-axis, and its terminal side is the place where you end the angle. Okay? So the terminal side of the angle is the place where the angle ends. Makes sense, right? Terminate. So initial is the starting, always on the x-axis. Terminal side is wherever you end up, okay, from that initial position. Okay? So we just talked about standard position, initial side, and terminal side. Okay? Now, if somebody said, I want you to draw an angle that is negative 135 degrees, any ideas what that's going to look like for us? Julia? Yes. Okay, yeah, so it's going to end up over here. So the difference when they give you a negative degree measurement is they're trying to tell you the direction they want you to travel around the circle. If they give us a negative degree measurement, we still put our initial side along this positive x-axis, and that's our 0, but we travel this direction, okay, clockwise, when it's a negative degree measure. Okay? And then you go clockwise that same amount that you would go if you were going counterclockwise, just the negative tells you to go this direction. So for 135, for negative 135, here's my initial side. And then, let's see, I know 90 would be here. How much more than 90 is 135? 45 more, so I know I have to be like out here. Okay? And that this is my 135 degree angle. Negative 135. Because I went the other direction. Is that okay with everybody? Okay. All right, so the confusion comes that there are infinitely many ways for me to name any of these angles. So this angle I just drew in red, if I told you to draw the negative 135 degree angle, there is one answer, and that red mark is the answer I would be looking for. That's it. But if I did a different approach, if I drew the angle for you, so if I had this drawn on the paper, and I didn't indicate any direction, so I didn't mark the angle one direction or the other, okay? So you had no idea if I got there by going a negative degree measure or a positive degree measure. There are infinitely many ways to name this angle. There are actually even infinitely many ways to name it, even if you know that I got there in a negative or a positive direction. But normally if someone draws on the loop, so if they draw this, like, oh, you know they went exactly that direction, it must be negative 135. Okay? If they drew it like this, you knew they went around the circle one time, and then went again to that mark. So you knew it's like 360 plus 135 degrees, which is 495, right? In the negative direction, so you call it negative 495. But without this marking in the middle, you don't know how many times they've gone around the circle to get there. You don't know whether they went the positive or the negative direction. Then there are infinitely many ways to name those angles, and all those angles that end at this terminal side would be considered co-terminal angles. Like co-captains of a team mean both of them share the same position, right? The captain position. Co-terminal angles mean that the angles share the same terminating side. That if you draw it without any of this stuff in the middle, so that nobody knows how you got there, that there are a bunch of different ways to name this angle. Okay? So if you know that you got here, okay, and you know that this is 45 degrees different from that or from that, so you know it's at the negative 135 mark, one way for me to name that angle would be to say, oh, that's negative 135 degrees. Okay? What's another angle that is coterminal with negative 135 degrees? Eric? Okay, so positive 225? Good. So somebody tell me, how did he come up with positive 225? Julia? Okay, so he could subtract the 135 from 360. Okay. He could also view this as 180 more, right, to end at 225. Can somebody give me another angle that is a coterminal angle with both 225 and negative 135? Alex? It cannot be 45, only because 45 would be here. So its terminal side would be over here. Okay, it's not quite enough. Dana? Good. Tell me how you got 585. Good. So 225 was indicating that many degrees, right? Her 585 indicates that same amount of degrees plus another 360. So it's saying go around a whole time, then go around that 225. Okay? Who can give me another coterminal angle with the ones listed up here? Addie. Okay, good. How'd you get negative 495? Good. So she said, okay, I'm just taking the 135 that was this direction, but I'm saying go around once, then go that 135. So 135 plus that one time around of 360 is 495, but all in the negative direction. Okay? So do you see how we could come up with infinitely many ways of doing this? Essentially, what would we be doing to come up with the infinitely many ways of doing this? What would we continue to do? Adding or subtracting 360. With the negative, you can think of it as subtracting 360, or you can take the negative off and be like, I'm adding 360 and making it negative. But either way, if you just continue this difference of 360, you would end up in that same position all the time. So all of those angles would be considered coterminal. They're not considered the same angle, but they end up in the same position, so then how we deal with the position would be the same. Okay? Uh-huh. Right. Okay, so it's considered an angle measure now because we're talking about number of degrees that go around here, and when we end, we do end in an angle. Okay? But she's right. We've always learned that once you got to 180, you just that was straight, and then beyond that, that didn't really make sense, right? So the issue becomes, how do we put it in a triangle, really, right? How can it become an angle in a triangle? So we're using the degrees to measure around a circle to give us a position that does build an angle because we use our initial side and our terminal side. But she's right. This actual angle that I visually with my eyes is not 585 degrees. That doesn't fit in the triangle. How would I find the sine, cosine, or tangent of that? And so we're going to talk about then, once it's in its standard position, what we compare it to and how we actually do the calculations at that point. The standard position just means that you started your initial side here and you've drawn it. So when they'll say draw an angle in standard position, but they'll give you a negative or positive measurement to draw. Matt?
Is there any name for
You would have to like declare in a problem like, oh, I'm measuring from the initial side being here. My angle is not in a standard position, something like that. So what you're going to see is always going to have it in the same type of position. Okay? And again, that's like a man-made. They started doing that way, and then that's how they continue to do it, right? Anything else about the vocabulary or how we measure this stuff before we move forward a little bit? And so we're going to get back to Julia's question about halfway through, okay? About like how do you deal with the 585 then? So I get we could loop around the circle and we could draw it, but then once you've drawn it, what does that really mean, and how do you calculate anything from it? We're going to get there. All right. So go ahead and sketch an angle in standard position that meets those requirements. So go ahead and make a sketch for part A and part B. So for 100 degrees and for negative 215 degrees. Here. Okay. So in order to draw our angle that is 100 degrees, we have our initial side here. Okay. And then to go 100 degrees would be to go about 10 degrees past 90. I don't expect anyone to be exact. We don't have like a protractor or anything like that, but something like that, and then we can indicate that's 100 degrees. Okay. And this time I did put this in here because I want people to know that that's what I'm measuring and not this way, now that we have this perception of how we could measure like from either direction, right? So then for negative 215 degrees, let's see, that's past 180. So if I put my initial side in, I know I'm going this direction. So I know to here would be 180 degrees. I need to go past 180 degrees. How many degrees past 180? 35. So not quite 45. So something like in here or something. Is that all right with everybody? And notice that I'm using a lot of reference points, my 90s and my 180s, to really help me realize how far away from something I need to be. Okay? All right. So now if you are given a diagram, can you figure out the angle measure? Okay? So let's start with part B, actually, right? Why do I want to start with part B? Any ideas? It's easier. It's like on the line, right? Which means like I just have to go some multiple of like 90 and I'll be there, right? Okay. So they clearly went this direction. So that tells me what about my angle? Negative. And how many degrees? 270. Okay. 90, 90, 90. Okay. Or 90 degrees past 180 if that's how you're thinking about it. Okay. So negative 270 degrees. All right. Now this one, much more difficult, right? I mean, I don't know. I could guess based on what it looks like. But if it's not drawn to scale, that could be harder. Maybe this then has some significance, right? Okay. Great. Good. How do you know it's 45?
Because from the y-axis to x-axis, that's a total of 90 degrees, and then the point 33, it's like, I'm trying to think how to say it. It's like 90 is divisible by 3, so each point you go off would be 34 degrees.
Okay. All right. So he's trying to look at if you connected the circle in here, how many 30-degree sections you would go up, or pieces of them. Matt?
You could draw like a square, and then the diagonal would like bisect the angle.
Okay. And how do you know that when you connect this, that this is a square? 3. So these are all 3. Okay. All right. Other perspectives, Alex? Like right here? Yeah, because the two legs are equal to each other, then it would have to be 45. Yep. Perfect. Okay. So there were several ways for us knowing some things about geometry to be able to figure out that that is exactly a 45-degree angle, not just because it looks like it's in the middle, because can I tell the difference with my eye between 45 and 46 degrees? Probably not. Okay. Which is why this information was necessary and was here to give us some mathematical reasons that support this 45-degree answer. Okay? Are we okay with this? So we can look at a picture and pull out the degree measure, or we can draw a picture that represents a certain degree measure. Okay? All right, so a little multiple choice question. Which of the following is not coterminal with the other three angles. So take a minute. You can work with a partner in your groups. All right. So 540, negative 540 is the one that doesn't belong. Okay, so now that we understand positioning of angles, we're going to approach Julia's question that came up earlier about like, okay, then what do you do? Like once you get this position, this is really a position, right? How does that become an angle in the way that we've always used angles, and how does that help us do anything with trigonometry? So we're going to look at this angle, okay? And here we're taking one that's not over 180, but still is an angle that tends to cause a problem. And we're going to talk about how we can relate these to other angles. So the first thing I want to do, draw it in yellow. I know yellow is not a good color, but I want it to kind of be the background, okay? Is for you guys to understand that if I do pick an angle position, okay, and this right here is the Greek letter theta, okay, that we saw before in our notes that we'll use for angles. If I pick this angle position, remember how we had the point in the last one, like 3, 3, and we were able to draw that right triangle and know, like, oh, that meant, like, this had to be 3 and this had to be 3 if I get to the point that's 3, 3, right? So whatever the coordinates are of this point that you can identify along your angle, then you can build a triangle, okay, with that, and that would tell you the two legs of the triangle if you knew the point. So if the point is some x and y coordinate, then you know that this is x and this is y. Like our point 3, 3 told us that had to be 3 and that had to be 3 to get to that point on our angle. Is that okay with everybody? Okay, now, that means that you have two legs of a right triangle. If you actually had numbers there, could you figure out the hypotenuse length right here? You could. Okay. Now, besides drawing the circle in to help us understand degree angle measures, it's also useful in helping us name some things. So when I drew this point, I drew it on the circle, okay? In the coordinate plane, the xy axis, that's how I knew this was x and this was y. If you don't look at the coordinate axis, though, for a minute, what do you call this line that goes from here and hits this point on the circle right here? The radius. So I'm going to call that r for now, okay? So everything is named based on the relationship between the coordinate plane and the circle, right? The x, y aren't just arbitrary, because if you pick a point, the horizontal thing is going to be x and the vertical thing is going to be y. Okay? And this is the radius of the circle. So when we found the sine of an angle before, so right now I'm calling this my angle. Okay? When we found the sine of an angle, you guys use your little SOHCAHTOA thing, right? Or I like the oh heck, another hour of algebra, right? Your sine is OH, which stands for what? Opposite over hypotenuse. In this diagram, if this is your angle, what's the opposite and what's the hypotenuse? Y over R. So another way to think about the sine of an angle is it's not just opposite over hypotenuse. That's when they draw the triangle like all by itself, right? The triangle has no context, so you use opposite over hypotenuse. If you have context on a circle or on a coordinate plane, you can now think of it, oh, it's the y coordinate over the radius length. If I know those things, I can draw my sine. Or you can draw in this picture and still think to yourself opposite over hypotenuse, okay? But it is going to be important for you to build the relationship between the sine being related to the y, okay? All right, what about for the cosine? How would we find the cosine of this angle? Adjacent over hypotenuse, which is x over r. And the tangent, yeah, y over x, opposite over adjacent, right? And then these other trig functions, just the reciprocals of those, right? Okay. Now, here's where the argument comes in. Let's say that this other point that's been drawn, this is technically how much they've moved, okay? A big angle, bigger than 90, right, to get to this position. But if I want to make a right triangle out of that position, I don't use this angle measurement, because can I use this angle measurement in a right triangle? No, it's already bigger than 90. I can't put another 90-degree angle in there with it. So once I'm at this position, if I want to build a right triangle, I actually build the triangle here. Okay. So what we do is we call this measurement right here a reference angle. And that angle is always this measurement between your terminal side of your angle, where you end up, and the x-axis. Because if you're going to make a right triangle from these positions, the only way to do it is going to be to take it back to the x-axis. Otherwise, your angle may be too big, right? So if you get that 585 angle and you end up in some weird place, you can still give it a reference angle by connecting it back. Now, some of you might be like, oh, that's not fair. You're not using the right angle anymore. Okay? So you're kind of right? I'm not using this big angle anymore. Now, all of a sudden, I'm like cheating a little and saying, well, you can just use this angle and get the answers for that angle. Like, why would you believe me? Okay? Well, let's say that, let me do a little bit of erasing here. Let's say the drawing that we did in the yellow was based on the angle being, really? 35 degrees. Not that you can read it, but let's say. Okay, so let's say that was based on the 35-degree angle, right? Then let's say their big angle that they drew in here, I'm going to erase all of this now so we can actually see it, is, I'm trying to pick so that it ends up being 35. What's 180 minus 35? 145? Let's say that this angle is 145 degrees. Right? So when I draw that 145-degree angle, how much is left right here to get to 180? 35. I did that on purpose because I said let's pretend that this one I had drawn in earlier was at 35. Would you guys be in agreement that if this is 35 degrees and this is 35 degrees, that these triangles right here, if they both are on the circle, are going to be congruent triangles? They're going to be the same size. Okay? This is still the radius of the circle, right? Which means if this point was xy, this is going the same distance, and this is going the same distance if those are congruent triangles. So it's still x and y. What's the only difference then? How do I end up over here and not over here? X is negative. It's got to be, right? That's the only way I fit in this position on the coordinate plane. So here's the trick to doing what we're going to do. We can find the sine, the cosine, and the tangent of 145 degrees by actually finding the sine, the cosine, and the tangent of 35 degrees, but the only difference is we have to make sure that we make this negative. Okay? So over here, whatever you got as the sine, the y over the radius, is actually going to be the same as the sine for 145 degrees because the y and the radius are going to be the same. But whatever you got as the cosine of 35 degrees, the cosine of 145 degrees is actually going to be negative compared to that, or the opposite of that. Okay? Yes? Right. So this is why, because it's not just a side length of a triangle anymore. So this is where we have to separate, like before someone drew for us a triangle on a paper and we were using a triangle. What we're doing here is saying we are now in a position. We're going to use our knowledge of how triangles work to come up with numbers in these positions. But no matter what those numbers are, if we know we're really in this position, the only way we could have gotten in this position in the coordinate plane is for this to be negative. So it's not really about the side length of the triangle being negative. We're using our triangle knowledge to come up with the numbers. But the numbers being negative or positive is all about the position on the coordinate plane and on the circle. Is that okay? Okay. So we're using the triangles to calculate something. The negative, positive are giving us direction in a different context. Okay? All right, so that means there's another angle over here. Okay? And let's say its reference angle is 35 degrees. Okay? Which means this angle right here in a positive direction, let's say I went like this to get to it, is actually 325 degrees. Is everybody okay with that? I would go 325 degrees to be at a position where 35 more would make 360. Okay? This is going to have the same distances again as those other two triangles, but this time the x is still just going to be x, but the y is going to be negative. Not because a triangle length is negative, but to get to that position on the coordinate plane or the circle would require a negative y coordinate. Is that okay with everybody? So we're going to get the measurements the same way we used to in the triangles, but now whether the measurements are negative or positive depends on position. So those angles are actually going to give us position, but we're going to use smaller angles to be able to work with our triangles. Okay? Is this all right with everybody? Okay, so we're trying to meld it all together. So you can build the same triangles and use all the triangle knowledge you've used before, but where you end up is either going to depend on how many degrees they tell you or whether they give you positive, negative stuff for your x, y coordinate. Okay? So let's see what that looks like. All right, so let's say they give you a point P, 8, negative 15, and they want you to find the value of the 6 trig functions at this position. Notice this isn't a triangle anymore. It's a position, and they want to know what the trig functions are. Okay? So first of all, 8, negative 15, which quadrant is it in? Little reminder. 1, 2, like our angles, it goes around this way. Okay? So maybe this quadrant naming actually makes more sense now that you learn how they do the trig degree measurements, because it goes in that same order. 1, 2, 3, 4. Okay? So it should be in quadrant 4, right? Because it would be 8, negative 15. So somewhere over here is this point, 8, negative 15. So when they say, tell me all the trig functions at that position, what they're telling me is if you have, like, draw your standard position angle. That means initial side here, terminal side was here. Now, technically, to get there, we went all of this way, but do I need to use that giant number to find the value of the trig functions? No. Instead, what I'm going to do is I'm going to draw in a triangle to give me some reference where I know that this is 8 and this is 15. If I was just drawing the triangle like Matt pointed out, they'd be positive lengths, 8 and 15. Because it's a position on the coordinate plane, I want to make sure I indicate which direction is negative. Julia?
How do you know that you went that way and not the actual angle?
You don't.
It doesn't matter.
I mean, it doesn't technically matter, no. Because either way, you'd build the same triangle and get the same trig functions.
So let's just find the values and just like label the A, B, and C. Is that fine?
So you don't have to label A, B, and C. So remember, we're finding the value of the 6 trig functions. So we're looking for sine, cosine, and tangent according to the angle that is built by this position. But whether it's this angle, okay, or this angle, like Julia said, how do you really know? You don't. Either way, we'd build the same triangle around that reference angle. And this 8 is the x-coordinate, but it's also the adjacent side to that angle. The negative 15 is the y-coordinate, but it's also the opposite side. And the hypotenuse over here, remember, is also the radius. And what is the length of the hypotenuse if you know the other two side lengths are 8 and 15? 17. And those of you that don't know how they got that so fast, that is a Pythagorean triple, or you can work out the Pythagorean theorem and figure it out. Okay? So now when you go to do sine, cosine, or tangent, there are actually 2 ways of doing this now. Going back to triangle knowledge and say, I know sine is opposite over hypotenuse. You can do it that way. Opposite over hypotenuse is going to give us negative 15 over 17. Or, how else did we say you could find the sine now? Look back at our diagram when we labeled the sine, cosine, tangent with x's and y's and r's. How did we say you could find the sine? Y over r. You knew the y-coordinate just from the given information, and if you really grasped onto this fast, you might not have had to even draw a picture to get the radius. Like if you understand it was just this squared plus this squared equals r squared. So you would get that 17. You could do y over r. Okay, same thing. So cosine, you're either doing adjacent over hypotenuse or you're thinking x-coordinate over r. Either way, you get 8 over 17. And then the tangent, you're going to get y over x, or opposite over adjacent, so negative 15 over 8. And so this is how you can have negative sine, cosine, tangent values, because it's about different positions on the unit circle, even though they have the same angle that you might have seen in a triangle before. And then you can find your cosecant, your secant, and your tangent, your cotangent, just by taking the reciprocals of all of those. Remember, reciprocal keeps the same sign, just basically changes our numerator and denominator. Michelle?
So doesn't the sine take the smaller angle?
Yes, you're always going to use this reference angle, which is the angle between the x-axis and where your terminal side ended up. Okay? And that way it's always going to be less than 90 degrees. You're always going to be able to build a right triangle by drawing the line back to the x-axis. And then that's how you'll be able to calculate all of your trig functions. Okay? All right, what about if they give us a point like 0, 1? Okay, so this is why it comes in handy to know the x, r, y stuff, because if they give you the point 0, 1, how is this different than the last one that we did? It's on the axis, so can you even build a triangle? 0, 1 is right here. I mean, I could go like that, somewhere random, but that's me putting in something random. That's not a connection to the position that I'm in, you know? So what do I do at this point? If I have to deal with opposite over hypotenuse and adjacent, that doesn't even make sense right now, right? But if you do it the other way, so again, look back at the original diagram, how do you find sine of theta on a coordinate plane now that you have x coordinates, y coordinates, and maybe a radius of a circle? How can you do that now, okay, if you can't use opposite, hypotenuse, and adjacent? So how do we find the sine? Y over r. If this is your point, then the circle would be like right there. This is the radius of the circle, okay, which means the radius is equal to 1 in this case, okay? Which means the sine is going to equal the y coordinate over the radius, which is just going to be 1. Okay? The reciprocal of 1 is still 1, so that's also going to be the cosecant. The cosine is going to be the x coordinate over the radius, or 0 over 1, which is 0. Okay? The reciprocal of that, or the secant, what happens if you take 0 over 1 and flip it over? What's that? Yeah, it's not possible, so we just say undefined. And our tangent of theta, which is y over x, right, is 1 over 0, which is undefined. And the cotangent, if we flipped over our 1 over 0, it would be 0 over 1, which is 0. Okay? All right, so we're going to stop here. We have a little bit more to do, but we'll just continue that tomorrow. So you don't have to do homework for tonight. Okay? You can do it tomorrow. You're welcome to start it if you want. I'm just kind of seeing where we're at. All right?